So let's get started. And the first talk is from Philipp de Vrese from MPI. Philipp, if you could share your screen.
That should have worked, I hope.
Yeah, perfect. Make full screen. Perfect. Excellent. Go ahead. Perfect. You know the rules, right? You've got, 10 minutes, and after 8 minutes, ESL will let you know. And
yeah. And, I'm very grateful for that reminder. Well, then I'm very happy to start off the afternoon block, presenting some of our results on the effects of temperature overshoot scenarios in the high northern latitudes. And the idea for that investigation came because we were really looking to find anything on how Arctic CO2 and CH4 emissions would behave not only in a warming scenario, but also in a subsequent cooling, because well, our current emission trajectory makes it increasingly likely that if we want to maintain global warming at a somewhat comfortable level, we might actually reach that only after such an overshoot. And then we also had the particular question whether such an overshoot could actually also entail legacy effects, or in other words, whether the steady state of the high latitudes may depend on the preceding climate trajectory. And for the investigation, we used our land surface model JS-Bach, driven with prescribed atmospheric conditions. However, we did not use our standard model, but we actually had to do quite a bit of model development, and we received also help from the CRESCENDO project, and that's actually the reason why I'm presenting here. So this is the scenario that we're looking at, and quite counterintuitively, so I've always managed to color the warming branch in gray and the cooling branch in red. I hope that's not going to be a big problem, but so the scenario follows SSP 5 8.5 until the year 2100, so raising atmospheric CO2 to about 1,000 ppmv, which results in an average temperature increase to about 4 degrees above pre-industrial levels. And as we really didn't have a clue how cooling back to the previous state would look like, we just assumed that the trajectory would essentially just reverse the increase prior to the peak. And now this is what the soil CO2 emissions behave in such a scenario. And now I'm giving the fluxes relative to the global temperature, so that it's very easy to compare if they are any different between the temperature increase and the temperature decrease. And what you can see is that the soil CO2 emissions, they actually have a very linear dependency on the global mean temperature. So roughly for each degree of warming, they increase by about 50%. And when you cool the Arctic back down, then they also decrease likewise. But when we started to dig a bit deeper, we actually found that the causative factors, they're anything but linearly depending on the temperature. So, for example, what you see here is the substrate availability, or more precisely, the amount of relatively easily decomposable organic matter that is stored within the active layer, and that increases when temperatures increase simply because the active layer gets deeper and the more formally frozen organic matter becomes available. And because that organic matter is decomposed during the warming, there is substantially less organic matter available for decomposition when we decrease the temperatures. And so in this offset should actually be also notable in the overall fluxes. But there is another important factor, and that is the fresh input, and that is carbon input, and that is essentially following the MPP. And as you can see, the MPP also increases quite a bit, A, because the warmer temperatures prolong the growing season, and B, because there's the CO2 fertilization is also quite pronounced in the model. But there's a third factor, and that is the vegetation composition, and that also changes quite a bit. So from less productive grasslands and shrubs towards more productive trees. And and these vegetation dynamics, they're quite inert. So when we cool the system, there's still, the tree cover is still higher, so the northern high latitudes remain more productive. And in the MPIs, and it just happens to be that these two factors perfectly balance each other, so that the CO2 emissions from the soils, they actually are very linear depending upon the surface temperature. Now the soil CH4 emissions do not have the same courtesy, so they're actually showing quite a hysteretic behavior. And you can find that for the same temperature range, so roughly here between 1.5 to 3 degrees above pre-industrial levels, you can either have the Arctic salts being a strong source for atmospheric methane when you warm the system, but when you cool it, it's actually a sink for atmospheric CH4. And so one of the most prominent reasons for that is the change in wetland area here, given sort of relative to the longitude and to the warming of pre-industrial. And what you can see is when we warm the system, the wetlands in the more southern regions actually kind of move or shift towards the more northern regions. And this is basically not reversed when we cool the system back down. And at the end of the simulation, we still have a much lower wetland fraction in the more southern region and in the larger wetland area in the more northern region. And just because there's more organic matter available in the more southern region, so especially in the Western Siberian lowlands, we also have this sharp decline in or the strong decline in the production of methane, which then also reflects in the overall emissions. So just to quickly summarize that part is, well, we found a very linear dependency in the soil CO2 emissions, but this essentially just masks that all the contributing factors are really all over the place. And for the soil CH4 emissions, we found that actually the hysteretic behavior is quite visible. And there the question is then, is that merely a transient phenomena? So would the simulations eventually converge to the same equilibrium state after an overshoot, or are there really any long-lasting legacy effects? And this we investigated at the example of the 1.5 degree target with 2 simulations. So one simulation just simply running up to the year 2035, and then afterwards we maintain somewhat steady atmospheric conditions. And the second simulation also comes to the 1.5 degree target, but only after quite a large temperature overshoot again. And this is then what happens in the Arctic. So what you see here are the 2 simulations, now just for one grid box. And the solid line shows you the simulation that was started with the conditions before the temperature overshoot, and the dotted lines start from the post-peak conditions. And so the red colors give you the summer and fall temperature at a depth of 1 meter, and the brown lines on the right y-axis, they show the total carbon content. And it is quite obvious that these 2 simulations, they do not really appear to be converging anytime soon. So even after 10,000 years of simulation, they're drifting further and further apart. And one reason for that is that when you start with the high organic matter concentrations prior to the temperature overshoot, this organic matter has an insulating function that reduces especially the soil temperatures during summer. And the lower temperatures mean that you have less soil respiration, and that allows the soils to continuously accumulate organic matter. And when you start from the slightly lower concentrations, so the soils are much warmer because the insulating effect is reduced, and this stabilizes and eventually leads to a continuous decline in the organic matter concentration.
2 minutes.
Thank you. Now the feedbacks that come after that, they're actually getting more and more complex, involving the hydrological cycle, but also the nitrogen cycle. And so I'm already on my last 2 minutes. I'll just skip the details. Just to show that we didn't manage to find the one single grid box where these effects actually matter, but that they're relevant across the entire Arctic. So this is now showing the difference again in the soil temperatures and the total terrestrial carbon, or rather the difference between the simulations. And you can see that when you start with the slightly lower organic matter concentrations after the temperature overshoot, you have consistently warmer soils ranging between 0.1 and 0.2 degrees, and you have about 40 gigatons of less gigatons of carbon in the soil. And if that sort of is not enough of an effect, we are also looked at the relative change in wetland area and in the soil methane production. And while the inundated fraction doesn't really change all that much between the 2 simulations, the methane production is actually about 12% lower when you start your simulation after the temperature overshoot. And that is, again, simply because sort of the correlation between organic rich soils and wetland areas is somewhat changed after the temperature overshoot. Yeah, so to summarize also that, yeah, we found that there are a number of feedbacks between the water, energy, and carbon cycle that actually allow for multiple steady states in the high northern latitudes. And here, these steady states do depend mostly, at least in our simulations, on the soil organic matter content that you start your simulation with, and these concentrations are substantially affected by any soil organic matter loss that arises from a temperature overshoot. And with that, I thank you very much for the attention.
All right, thank you, Philipp. So there's one question in the chat from Pat Hyder, although, I mean, Pat is saying the question is just for the chat. Not sure how relevant is it for your talk. So, okay, I'm gonna read it out anyway, because this is the only question we have. So Pat is wondering about the transfer of carbon from trees to soil each autumn in mid and high latitude with leaf shedding of deciduous trees is compared to the other carbon transfer from soil and trees, and whether this is represented adequately in the model.
Yeah, so I'm not sure whether we do a very good job at representing this, but we have this effect, and that's actually also part of why the soil or why the methane emissions behave so differently to the CO2 emissions, is because we have most of the carbon input, so from leaf shedding, actually after summer, so during fall, and this is the time when the wetland area is comparatively small, because we have the largest wetland area or the largest wetland extends just after the spring snow melt season. So the increase in inputs that stems from the increase in primary productivity also happens to be really at an unfortunate moment, so always coming after the wetlands just disappear. So I mean, we have this kind of temporal offset in the model. I'm just not sure whether it's perfectly well captured.
There's a few more questions that just came up now. So one from Chris Jones about the methane emissions. Are they coming from wetlands or permafrost or both? And do they behave differently under overshoots?
That again, sorry, I didn't catch the last part. I was reading, my fault.
So the methane emission, do they come from wetlands? Do they come from wetlands or permafrost or both?
Yeah, I mean, so in the model, it's all the same. So we try to do a bit of a separation between wetlands that are formed due to ponding at the surface and the wetlands that form in saturated soil. So for one, we use a top model based approach, just redistributing the grid box mean soil moisture, and we also have a wetland extent scheme, or short the WEED scheme, and that represents this ponding. So these are the two types of regions where we can have methane emissions, but really sort of the more permafrost specific processes, such as I don't know, thermokarst lakes or something, we unfortunately could not represent in the model. So yeah, so methane comes from saturated soils, but also inundated areas or flooded areas.
I'll take one last question from Peter Cox. And I mean, sorry, Colin, your question came too late. So maybe Philipp will answer in the chat. So question from Peter Cox. What's the main mechanism for the hysteresis in the methane emissions? Is it linked between soil carbon and soil hydrology? So the hysteresis, so during the overshoot, there's a number of factors. So one is, and the most prominent just being that the wetland area is very different in the warming branch than between the warming and the cooling branch. So because the permafrost kind of acted, at least in the past, in our model acted as a lower boundary, so it strongly inhibits drainage. And so when the permafrost disappears, this boundary also disappears, and the soils drain much more readily. And it just takes a lot of time until the permafrost reforms after the overshoot. So part of this hysteresis, or this pronounced hysteresis-like behavior, is actually transient. But there's also, as I showed on the later slides, there's also really a non-reversible shift in the wetland area and in the correlation really between the soils with high organic matter content and the wetlands. So this is what really drives this permanent hysteresis in the end. Excellent. Okay, well, thanks so much again. And I think it's time to move to the next talk from Mark Williamson, sorry, from University of Exeter. Mark, if you could share your slides.
No worries.
Excellent. Yeah.
It's up, is it?
Yeah, just make full screen.
Oh, yeah. Yeah, brilliant. Okay, hi, everybody. I'm Mark Williamson. I'm just going to plug a deliverable we've just submitted as part of work package 8. So this was a review on emergent constraints on climate sensitivities. It's in press in Reviews of Modern Physics. So hopefully that should be out any week now, but it's also available on the Los Alamos preprint archive. The address is in the bottom corner there. So this was work with Chad Thackeray, Alex Hall at UCLA, Peter Cox, also Exeter, Chris Huntingford at CH, and Femke, who's also at Exeter. So just to give you, for those that don't know, what emergent constraints are, they're basically a way to constrain a real world unknown using a model ensemble and observations. So this schematic is probably most useful. What you're looking for is something you can measure in the real world on the x-axis, some trend or variation, and you want to relate it to something you want to know in the real world but you can't measure, so some future projection or some system sensitivity. And the way you do this is by looking in a model ensemble, for example, CMIP 6, CMIP 5, etc., and looking for a relation between this future unknown and the thing you can measure in the real world today. So each of those dots are an individual climate model, and you want this thing called an emergent relationship, which is basically just a low-dimensional relationship in a model ensemble between something that you can measure now and something you want to know in the future, but you can't measure in the real world, but you can in the models. So the nice thing about this is, what if you can find one of these relationships, you can measure the observable in the real world, this blue line, and just read up and cut along and read off on the y-axis what this implies with the uncertainty in the observation. So this read off on the y-axis of the real world is the thing called the emergent constraint. So it's the result of applying the emergent relationship with the value of the observable, and that implies constraint on the real world value of the system sensitivity. So just to give you a concrete example of this, the oldest and best confirmed emergent constraint is this one by Hall and Q back in 2006. This was originally on the CMIP 3 model ensemble. So they were interested in the snow albedo feedback, particularly how strong the snow albedo feedback would be under climate change. So the observable they measured in the models in the real world was the snow albedo feedback strength against the seasonal cycle. That's something you can measure in the real world. And it's something you can measure in the models as well. So the individual dots are the models, and you can run climate change simulations with models and measure the climate change, the snow albedo feedback due to climate change. And not surprisingly, really, because it's a fast feedback, you really get this one-to-one relationship. So you can measure in the real world the snow albedo feedback is about 1 watt per meter squared per Kelvin. And it implies the snow albedo feedback under climate change is also about 1 watt per meter squared per Kelvin. And this is really well confirmed. It's kind of quite intuitively obvious as well. It's been confirmed in CMIP 5 and CMIP 6 as well. But since then, there's been a whole bunch more emergent constraints that have been found. These are a few I've just taken from this review that's on the archive. So we've got ones on climate sensitivity. They've been very popular. Carbon cycle, cloud feedbacks, the cryosphere, the hydrological cycle. And we've got a comprehensive table for all the ones we know about up to a few months ago in this article. Again, plugging it, that's the address. So, okay, how might low-dimensional emergent relationships appear in ensembles of complex models, given climate models in the real world have very high-dimensional parameter spaces, and their responses are generally functions of all those parameters? Well, you could say the null hypothesis is they occur by chance and they're not indicative of deeper predictive mechanistic relationships. And this is in particular a real danger in small ensembles of models with high numbers of outputs. Just data mining in a small ensemble, you will find high correlations just by chance. So there are real dangers of data mining and P hacking. There are also dangers if you don't, in the statistical assumptions and statistical errors, you can get false positives again with that, and there have been in the past. But on the flip side, there's also the non-null hypothesis that they are indicative of approximate deeper mechanistic relationships. And this shouldn't really be surprising because, of course, in the real world, we do see these approximate relationships, even though the real world is this highly complex, infinite parameter space thing. But you do see simple relationships between things, physical laws, for example. It's the reason why science works. And certain responses may be dominated by a few degrees of freedom. This giant parameter space effectively becomes very small if you look at particular responses. So this can happen when a particular response becomes sensitive, close to an instability, for example, or when the range of values of one process in the model ensemble is large relative to the other processes controlling that response, i.e. one process really controls the response to a good degree, or that other parameters are relatively weakly coupled to that response. So this is something we go through in the review. We also talk about how might emergent constraints go wrong and how you might guard against it. So to guard against chance relationships, this data mining thing, you can use a predictive theoretical basis that can be independently falsified. And so it makes predictions outside of the emergent relationship. And this is the approach we've been following quite a bit in Exeter. So you can also have, of course, overconfidence in constraints, and you can guard against that by taking into account all sources of uncertainty. They can also go wrong because the models have missing processes or feedbacks. There's not a lot you can do about that. Also, you can have compensating errors in models. If you have compensating errors in models, the functional response in the emergent relationship might be spurious. And there may also be errors in the observations, or the observations are not directly comparable to what the model is producing. So just because the model spits out like a temperature field doesn't necessarily mean that's what you measure in the real world. So it's another thing you've got to be careful of.
2 minutes.
Thank you. So emergent constraints can be a powerful tool to reduce uncertainty and promote understanding of the important processes and a variety of climate projections, provided you're aware of all the possible pitfalls. And I think we're getting to the stage where this awareness of these pitfalls is becoming more apparent. And there has been data mining in the past, but people have been fighting back against that rightly. And the emergent constraints are hopefully becoming more understood. And as these pitfalls become more understood, it should lead to emergent constraint research becoming more rigorous and more useful. So just to quickly give you an idea of what's in this big review, we have a section on how relationships and model ensembles might emerge. We have a theory, a section on the theory. We have a section on how might they go wrong and how you might guard against it. We have a section, a big review of all the emergent constraints found in the Earth system so far. We have a section on the statistics, a section on the outlook as well. So we're hoping this is going to be really useful to people working on emergent constraints, thinking of working on emergent constraints, who are just interested on where we're at right now. And I think that's all I wanted to say. So thank you.
All right, thanks, Mark. Okay, so there was one kind of a common question from Pat in the chat box, which has been answered by Peter already. So I'm gonna jump to the next one from Colin. Do you know whether modeling groups now tune their models to get EMC right in the way they do with present-day observations?
Sorry, what was the observable you think?
Do you know whether modeling groups now tune their models to get EMCs? I guess you mean emerging constraints, ECs, emerging constraints, right, in the way they do with present-day observations. Yes, he meant ECs, sorry.
Not that I'm aware of. So Chad Thackeray and Alex Hall have been working on the snow albedo feedback for a long time. That was the original emergent constraint. And talking to them, they're really frustrated that the modeling groups haven't changed anything at all. It's exactly the same spread each time. So in that case, I'm guessing not. In other cases, I don't know.
Excellent. Thanks, Mark.
Okay.
Okay, so we'll move to the next talk from Lisa Bock from DLR. Yeah. You can make full screen. Yeah.
Okay. So hello, my name is Lisa Bock. I'm from the DLR, the German Aerospace Center, and my talk is about quantifying progress of climate models across different CMIP phases. So CMIP stands for the International Coupled Model Intercomparison Project and is, as part of the WCRP, one of the crucial elements of climate science to understand the past, the present, and the future climate. The current phase is the current running phase is phase 6, CMIP 6, called CMIP 6. And its setup is like that. First of all, there are 5 common experiments defined called the DEC experiments and the historical simulation. And they are the entry card for the CMIP endorsed model intercomparison projects called MIPS. You see them on an overview on the right side here in red. And they are designed by the scientific community to address a large range of specific scientific questions. So then 40 modeling centers worldwide participate in CMIP 6. The number, for example, of models has doubled in comparison to CMIP 5, and the expected amount of data is a challenge for the entire community. So for this study, we used the ESMValTool, which aim is to ensure a rapid and comprehensive evaluation of the models with observations, and we hear more about the ESMValTool in 2 talks later in this session. When now applying the ESMValTool to the CMIP data, we get an overall overview about the great improvements of the model ensemble. So we see here the geographical pattern correlation between models and observations for the annual mean climatology. So the results are shown for individuals, CMIP 6 in red, CMIP 5 in blue, and CMIP 3 in cyan as short lines, along with the corresponding ensemble average as a long line. And the correlations are shown between the models and the reference observational data set. And additionally, a correlation is shown between an alternative observation and the reference data set as a gray circle. So there are fields that have been already quite well simulated since CMIP 3, as the near surface air temperature and the TOR outgoing long wave radiation. And for others, we could see large improvements as for precipitation, TOR, shortwave cloud effect, and sea level pressure regarding the correlation, but also regarding the multimodal spread. And also a quick overview of the model performance for more variables. Show this portrait diagram. And the quality of simulation is summarized in a single number, and here as a root mean square difference to reference data sets. So positive values in reddish indicate a model performance worse than the median root mean square difference, and bluish colors and negative values are performance better than the median root mean square difference. And what we clearly could see is that the number of blue colors increases from left to right, from CMIP 3 to CMIP 6 for several atmospheric variables. And we could also say that the Earth system models are improving when looking to the carbon cycle. So in the upper left panels, we see the time series for the column averaged CO2 for CMIP 5 and CMIP 6. And the model spread in CMIP 6 is similar to CMIP 5, but the multimodal mean in red agree much better with the observation in black. And one reason, therefore, is a better representation of the seasonal cycle, as you see in the panels below. So again, the performance metrics shows improvements for all carbon cycle variables from CMIP 5 to CMIP 6. So we have more blue colors for CMIP 6. On the next slide, we see the geographical pattern of the near surface temperature of the CMIP 6 multimodal mean in the upper left panel. And the CMIP 6 ensemble is able to simulate the key characteristics of the observed global surface temperature pattern quite well, which is the dominant feature is the zonal gradient from high values at the equator to low values at the pole. And the other three panels show the near surface air temperature bias of the CMIP 6 multimodal mean in the upper right panels, of CMIP 5 in the lower left panel, and CMIP 3 in the lower right panel. And all CMIP and the bias is shown in reference to the ERA5 dataset. So all CMIP ensembles reproduce the large scale annual mean pattern quite well, but in some regions there are some long-standing biases, as for example in the high elevation regions, near the ice edge in the North Atlantic, and over the upwelling regions in the subtropical ocean. And when we look to the high-res MIP simulations, now in the lower panels, we could compare the high-resolution versions of the high-res MIP models in comparison to the low-resolution version of the high-res MIP models on the right lower panel. And we see a decrease in this long-standing bias regions as the ocean upwelling regions, the high elevations, and also over the Northern Atlantic. So now we see the time series of the anomalies in annual global mean near surface temperature for the multimodal mean of CMIP 3, CMIP 5, and CMIP 6. The reference period is 1850 to 1900, and the observational data set in black is headgroup 4. So the simulation of the overall warming trend is quite similar for all CMIP phases, including an accelerated warming beginning in the 1970s and a temporary cooling that follows large volcanic eruptions. But we also see that CMIP 6 tends to simulate a reduced warming after 1950, which is partly related to an overestimation of the cooling in response to large increases in anthropogenic aerosol emissions. And on the other hand, the very high warming rates in the last part of the 20th century of some CMIP 6 models end up with a too large temperature trend, and this is also reflected in a very large climate sensitivity. So which brings me to the next slide. Climate sensitivity is one important metric to evaluate the sensitivity of the models to four things, for example, the changes in CO2. And it is defined as the change in the global mean surface air temperature as an answer to a doubling of the atmospheric CO2 concentration. It's an important metric for assessing the future warming sensitivity of the climate system and to increasing concentration of CO2. And as you may have noticed already, this is a hot topic regarding the new results from the CMIP 6 models. And in the graphic, you see the blue bars, which show the estimated range in ECS and former assessments, partly based on the former CMIP phases. And we see that the estimates of the ECS have not changed in the last decades, and there was also no decrease in uncertainty. And now some CMIP 6 models reach higher values. CMIP 6 models here in the colored signs on the right side. And yeah, this higher values in some CMIP 6 models leads to an increased model range of ECS. And first studies indicate that the uncertainties in clouds are the main factor.
2 minutes.
So I come to my summary. Then more than 40 climate models link centers worldwide participate in CMIP 6. The ESMValTool enables a comprehensive, rapid, and reproducible performance assessment. And when quantifying the progress of climate models across different CMIP phases, we see significant improvements from CMIP3 to CMIP6 in model performance. We also see that high-resolution models reduce long-standing biases in ECMs and increase ECS in more complex ECMs. Okay, thank you.
All right, thank you, Lisa. I have a couple of questions in the chat box. One from Michael Schulz. How do you know that the aerosols relative forcing is larger in CMIP6 than in CMIP5 or CMIP3?
I think yeah, there were studies where we compared the aerosol, the answer of the increases of aerosols. I think Chris Smith has done the study.
Okay. There's another question from Richard Woods. Have you looked at any subsurface ocean variable, like AMOC, thermocline structures, and so on?
No, not in the study.
Not okay. Another question from Colin. High-res MIP improvement to me look to be largely only in the ocean upwelling regions. Do we know whether this is primarily thanks to ocean model resolution increase?
Where? Sorry, I missed the beginning of the question.
Sorry, the improvement in the high-res MIP simulation, the improvement seems to be largely in the ocean upwelling regions.
Mm-hmm.
And do we know whether, oh, sorry, the chat box is moving. Do we know whether this is primarily thanks to ocean model resolution increase? Do we know?
I'm not sure, but
not sure.
Yes.
Okay. Now the next one is still about emergent constraints. I think that's it. Thank you, Lisa.
Thank you.
Thanks. Very good. Okay, we'll move to our next speaker, which is, if I'm correct, yeah, Stefan Lange from PIC. Welcome, Stefan.
Hi.
Okay.
Yeah, hi. Can you see my?
Yes, perfect.
Slides?
Perfect.
Okay.
Go ahead.
Yeah, hi everyone. I'm Stefan Lange. I work in the intersectoral impact model into comparison project, in short EasyMIP. So that's a project where we try to bring together the impacts modeling community and do harmonized impact simulations and projections. So it's a bit like CMIP, but for the impacts community. And today I want to show you as an example of a study that we did within this framework within EasyMIP. And the title of the talk is like the title of the paper, is projecting exposure to extreme climate impact events across 6 event categories and 3 spatial scales. So this is, I want to stress this, this is really real collaborative work. There are 43 authors in total on the paper, and each of those authors is, almost everyone is either an impact modeler or a member of the EasyMIP cross-sectoral science team. So yeah, the research question that we tried to answer here is, how will the exposure to extreme climate impact events change in response to global warming? And we wanted to answer this question. We're not the first ones to ask this, but we wanted to answer it using EasyMIP 2B, data from EasyMIP. And EasyMIP is organized in simulation phases or simulation rounds like CMIP. So here we used data from the second phase of EasyMIP, EasyMIP 2. And the B is for the projections part of that. So yeah. We cover, in this study, we cover 6 different extreme event categories: river floods, tropical cyclones, droughts, crop failure, wildfires, and heat waves. And we are able to do that because we have many different impact models in or impact modeling teams participating in EasyMap. We have hydrological modelers, tropical cyclone modelers, crop modelers, vegetation modelers, and then for the heat waves in the lower right here, we just use the climate model output directly to compute an index for that. So the analysis framework that we used for this study is, yeah, was a bit challenging to find a good metric that we could use to measure or to quantify the exposure to these different types of impact events, because a tropical cyclone is a very different thing from a wildfire, for example. So it was challenging to find a way to measure this with the metric that can be aggregated across those different event categories and that can be compared and works for all of them. So yeah, because those different event categories, all kinds of events, they differ in the quantities and units that they are usually measured in. To kind of unify this, we decided to define thresholds for each of those event types, and then said that we are only going to consider events that are stronger than whose strength exceeds a certain threshold. Then they also occur on different time scales, and there we decided to look at the annual time scale and just ask the question: does in a given year does an event occur in a certain place or not? And they also have very different ways of affecting us. They destroy infrastructure, or they lead to morbidity, or they have very different kinds of impacts. But something you can basically always do is you can always draw a map of a spatial map of which areas were affected by the event. So that's what we decided to use. We just measured the spatial extent of the exposure. So putting all of this together, this is our metric. The metric we used, it's the land area flooded or burned or affected by an event at least once in a year due to a river flood or wildfire, and so on, event of a magnitude greater than a threshold value that represents what was extreme under pre-industrial climate conditions. So that's an important detail, that the thresholds were defined based on PI control, climate simulations, and impact simulations driven by those pre-industrial climate conditions. Okay, and now I'll walk you through an example of results. So this is for river floods. Here we used, we considered only floods that had magnitudes greater than the 100-year return level under pre-industrial climate conditions. And we analyzed simulations done with 4 climate models combined with 8 hydrological models. So in the plot on the right, each color represents a climate model, and the different lines then represent results for different model combinations. And very important is that in our future projections, we only varied climate and everything else. So in this case, for example, the flood protection levels, they were kept constant. So we did this to isolate the pure effect of climate change. And then we pooled the results. So we used the RCP projections from CMIP, bias adjusted those, and then ran the bias-adjusted data, use that as input for impact projections with those hydrological models. So we actually have transient simulations, but we wanted to analyze those in terms of global mean temperature change. So on the x-axis in this plot, you see global mean temperature change relative to pre-industrial. So we basically pooled the results, put them into temperature change bins, and yeah, so that's what you see on the x-axis, global warming basically, and then on the y-axis you see the change in the global land area that is annually exposed to river floods, and that the unit here is it's the percentage of the global land area.
2 minutes.
Thanks. And so we did this for all 6 event categories. Here you see the results. River floods you already saw, and basically in all cases we see an increase in the global land area exposed. In some cases, for example, here for droughts, the hydrological, or the more generally speaking, the impact models contribute a lot to the overall uncertainty. In other cases, it's more the climate models. But yeah, those are the global level results. And then we also looked at grid scale results. That's where we actually did the computations. And so I'm going to, I think, jump over those, or just quickly say that we find the largest increases in exposure in low latitudes and low altitudes regions. We combine this with population maps to get the number of people exposed. And there we find the largest increases in the low latitude, low altitude regions, which are strongly populated, of course. And we also looked at the country level and compared changes in exposure with GDP per capita, and found that for 2 event categories, crop failure and heat waves, we find a relationship that shows that more wealthy countries are expected to see less of an increase in exposure. For the other 4 categories, there is no relationship really. And yeah, to wrap up, if you're interested to learn more, there's the paper published in Earth's Future. We also have a simple language article on Easypedia, which is the kind of outreach platform of EasyMIP, where we try to explain our research in layman language. There's also visualization of the results in the census toolkit. There you can explore the data, and there's a follow-up study currently in preparation about which looks at the same data, but analyzes the data from an intergenerational justice point of view. Okay, that's the end.
Right. Thanks, you, Stefan. I have a couple of questions in the chat. One from Klaus Wyser. Do the threshold for extreme events change over time?
No, we used fixed thresholds. So yeah, we which is then, I guess, equivalent to assuming no adaptation. So we kept everything, as I said, we kept everything constant. All the socioeconomic data, all the management, for example, agricultural management options, and we all kept all of that constant at present day to really see the.
Okay, so the sub question from Klaus was that so like a heat wave today could be like a normal summer in the future, essentially, right?
Yeah.
Yeah, okay. Another question from Colin. Is there any work in EasyMIP on air quality impacts, on health?
Mm-hmm. I was recently involved in where we wrote a proposal together with air quality modelers. So this may come in the future, but currently we don't have an air quality branch yet.
All right, okay. One last question from Sophie Eden. Have you done any sort of days affected analysis
Number of days affected?
Yeah.
No, we only looked at, so we wanted to see, because, you know, some events, they can occur multiple times a year, but some usually only occur once per year. And we wanted to harmonize that. So we aggregated everything and just measured the area, the land area that was affected at least once per year by an event of a certain category. So yeah, unfortunately, I don't have number of days affected or something like that.
All right. Well, actually, I had one. I mean, short question as well, which is not in the chat. You say that the impact models include changing climate in the future and nothing else. I mean, do they also include changing CO2?
Oh yes, yeah,
okay,
that's true. Yeah, the CO2 fertilization effect, yeah, is, for example, in the crop simulations, it's in there, yeah.
Okay, excellent. All right, well, thanks so much again. We'll move to the next talk from Axel Lauer from DLR. Axel, are you with us? Yeah, excellent. Go ahead.
Okay, all right. So hi, this is Axel from DLR in Germany. And I'm giving a rather brief general overview on the ESMValTool version 2. That's a tool to analyze and evaluate CMIP models in a relatively easy and convenient way. And here I listed only the key people doing the CRESCENDO work. But of course, this has been a large community effort. So behind this ESMValTool development team, there's literally dozens of other people who did significant contributions to the development of ESMValTool version 2. In the beginning, when we started, we had ESMValTool version 1.0, but we knew CMIP 6 would be coming up with more models, more model experiments, higher complexity of the models. So we expected a huge increase in the data volume, and we needed to redesign and rewrite quite a few parts of the ESMValTool to actually handle that challenge of analyzing and evaluating the CMIP 6 models. And for that, we used infrastructure used for modern software development. So we moved to GitHub, which allowed us to develop with a huge team and share code. We moved to an online documentation system that made it obsolete to always edit and hack a Word document, but instead we now can update the user's guide basically automatically. And we also introduced new tools to ensure code quality and automated testing. So the aim of the ESMValTool itself hasn't changed. We want an easier and faster evaluation of the complex Earth system models, in particular of the CMIP models. And we want to be able to get a fast overview by applying a set of standard diagnostics from literature. One very important thing is to improve the general quality for model evaluation. And here I would like to point out what's written here, traceability and reproducibility of the results, which becomes more and more important because we have to know which data have been processed, which processing steps have been applied, and how did the results come about. So we have to be able to trace back what happened to the data. And we also need a system that's easily expandable with other existing software packages. So I wrote here one example from NCAR, the Climate Variability Diagnostics package, to name just one example. And we needed coupling to the Earth System Grid Federation to be able to analyze the CMIP 6 output in a very timely manner. So whenever the results have been published to the ESGF, we would be able to look into them. So the tool has been released in August last year, and that was a huge community effort. And we had a pretty rapid development since the version 1, supported by a number of projects, also CRESCENDO, of course. And we now provide a well-tested tool that ensures end-to-end provenance. So we have traceability and reproducibility of the results. And the tool has been successfully used for contributions to the next IPCC 6 assessment report. And it has been documented in a number of scientific papers. So here you see an overview. 3 of those papers have been published last year. 1 is still in revision. And 1 paper deals with the technical overview. So if you want to get to know the technical details, you can look into that. And 3 papers are describing and giving examples of new diagnostics that have been implemented. And just to put things a little bit into perspective, what that actually means. So we had about 200 developers from over 60 institutes contributing to the code. And in total, we had 17 funded projects. And I just put a few logos of those projects here around so you can see what besides CRESCENDO was done in other projects. And to come to release of version 2, that actually took about 3.5 years of work. We had 8 coding workshops. We have hundreds of pages of documentation. And just to put a number on it, we have a bit more than 500,000 lines of code that went into ESMValTool version 2. So here is an overview on the workflow of the new version. The core functions have been completely rewritten. We have much better performance by using state-of-the-art libraries, such as the Iris, for example. And we have a much easier installation and configuration, which makes the thing a lot user-friendlier than it used to be before. And in this schematic, you can see what happens. So we have so-called recipes that would define the input data and also all the pre-processing steps, configuration options, and the diagnostics to be run. And then that would go through a preprocessor that applies common pre-processing steps, for example, regridding or creating a common data mask for missing values. And that would be fed into the diagnostics that would then create the scientific output, which could be NetCDF files or plots. And of course, we have information on the provenance. So just some examples from the new diagnostics that are available in version 2. Here's an overview of some of the large-scale diagnostics. Yesterday, Klaus already briefly introduced the Single Model Performance Index, SMHI, which is a nice way of getting an overview how your model or model configuration performs compared to other models across a number of variables that you can choose. And I also picked 2 plots from the paper that Lisa just introduced briefly, where we looked at 2-meter temperature and also the temporal evolution of 2-meter temperature. Here are some examples of diagnostics for emergent constraints and also for analyzing future projections from Earth system models. So here is an emergent constraint, and I'm kind of happy that Mark already nicely introduced what an emergent constraint is. So here you see one for the effective climate sensitivity, where we look into differences in cloud cover between the tropics and southern mid-latitudes and established a relationship with the effective climate sensitivity here. Here you see an example of how to analyze climate projections. Those are changes in global average surface temperature over a variety of models and different emission scenarios. And here's an example for an analysis in the trend of Arctic sea ice. Then we also have a couple of new diagnostics for regional model evaluation and extreme events. And here on the left, you see the standardized precipitation index. In the top, the absolute values from the models, and in the bottom, the differences to a reference data set, where you can look at how well those events are being simulated. Or for example, here is something that looks into heat waves. Here you see the change in the number of summer days per year between RCP 8.5 and present day. And we also have a set of about 10 different indices for precipitation and temperature related extreme events that can be analyzed. And here is an overview of how that looks like if you just want to get an overview.
2 minutes.
So to summarize, the ESMValTool is ready and can be applied for relatively fast and easy routine evaluation of Earth system models, including what becomes more and more important, in my opinion, is traceability and reproducibility of the results. So we have a full provenance record for all results. And it has been coupled to the ESGF, so we can provide a pretty rapid and comprehensive assessment of the models as the results are coming in. And that has been an international community effort, and the version is publicly available, so you can download and try. We have a lot of also technical improvements in version 2, which is a lot faster and a lot easier on memory, for example. We have higher code quality, automized code checking, just to mention a few, and a documentation that's always up to date, as it's updated automatically once new contributions are coming in. And the tool has been used in support of the upcoming IPCC assessment report for at least 2 different chapters. So just a brief outlook. With the end of Crescendo, this isn't the end of the ESMValTool. The development team is still growing and will also continue beyond the end of Crescendo. So currently we already at release version 2.2 as of February this year, and a new release is planned for summer. We have a number of different resources. So we have the code is available at the GitHub repositories. We have an online documentation on the technical aspects and also the scientific aspects of the diagnostics. We have a tutorial to make it easier for new users to get into using the tool. And of course, we have a web page. And with this, I would like to thank you.
All right, excellent. Thank you, Axel. Questions? Well, first, a comment from Colin. Big thanks to the team involved in the ESMValTool development. It's been a fantastic effort and a real success for Crescendo.
Yeah, so, thank you.
But he has a question though. Are there any plans to enable the ESMValTool to analyze regional climate models, example in Codex?
Yes, that's actually a long outstanding thing that is still to be implemented within other projects, and that will definitely come.
Okay, excellent. I had a question as well. I mean, do you know how many users of the ESMValTool you have? I mean, non-developers. You can track of how many people are using the tool?
That's actually a difficult question because we don't really track people, because anyone can just download it and install it. So what we see is mostly feedback when people have questions and they're coming to us to ask, like, how do I do this or how do I do that? That's when we started developing the tutorial, because the number of people using it seemed to increase, particularly with CMIP 6. That seemed to generate quite some interest, but I don't have numbers because we don't keep track. We don't ask people to register. Anyone can just download it and try it.
All right, okay. There's a few more comments, but I'm not sure there's any question. No, all right, excellent. Thank you. Yep. We're moving to the next talk from Valeriu Predoi from NCAS Reading.
Afternoon, guys. Before I start, I actually wanted to answer the previous question. So you can use GitHub statistics. There's metrics that can tell you how many people, how many individual clones were done from the repositories, because we have ESMVal core and ESMValTool. So you can ballpark, but it's a wide margin of error. So I would say in the hundreds. But then you also need to think about the people that have, taken it from whoever downloaded it or cloned the copy and used it. So that's hard to answer, but it's in the hundreds at least. All right, I'm gonna quickly share my screen, and I'm gonna select the screen, enter screen. All right, can you see the screen?
Okay, I can see my name.
Okay, well, so I'm gonna fly through this because it's not actually a presentation. I'm a software developer and a core developer of ESMValTool. Being a software developer, a software engineer, I don't really like slides. So you get a README from GitHub from me with active links. All these stuff that Klaus and about, you can access them. So all the stuff about ESMValTool. You can access them if you just go to the first entry point, which is the README. There's one thing that I added to the README, which is not in the ESMValTool README. It's a really nice Porsche 911 here. I'll get to it in a second. So what I'm gonna try to tell you and make sure I get the message done is the fact that ESMValTool has evolved, overlapping in good measure with the CRESCENDO time span, but also independently of CRESCENDO, has evolved into a mature and solid software package. And I'm gonna tell you what the metrics for a solid software package are and how we actually gonna prove that we actually have a solid package. So as usual, what you'd expect from a software package, you'd have a decent documentation, and we have this, and you can click on this and it takes you to the documentation page, which is on Read the Docs, which is a standardized way of, we have ESMValTool and ESMValCore. You probably know what ESMValCore is. Axel has talked about it. I'll show you in a second. So it's a well-detailed and well-explained documentation. We're still working on it. We might get to a point where it's actually too much, but we're trying to balance the amount of information versus the amount of text. So yeah, but it's in quite a decent shape. Then we have the website that Axel showed you, which is a pretty nice website. It's modern. It looks swanky. And you have here all the really nice stuff like, dynamic link documentation. There's a gallery. I'll tell you in a bit about the gallery. The crap like license and references and roadmaps. And as you have a link to the theme and where to download it off GitHub. So it's a very nice website, courtesy of DLR, guys. Then where we host our project is the ESMVal group is a whole project. It contains ESMValTool, ESMValCore, and a few private stuff like the development for the IPCC work. It's on GitHub. And you can just go here and, your usual GitHub. We have issues, we have pull requests, you have insights here. You can see who's been contributing, contributors here. It's slowly loading, crunching the latest. What's going on with GitHub? See, that's activity, who's been working on it. And finally, we have a nice gallery which contains the plots, the images of the diagnostics that we have in the library. And these are all pretty sciencey plots that I don't really know much about because all I'm doing is coding and making sure that the package works. But yeah, you see all this fancy stuff, sciencey stuff. So introductions is gonna go over because you guys know what the ESMValTool is. You've been told. So one thing that I wanted to show you how the package works. Oh, and before that, we in the README have all these badges and all these really nice. It's maintained. It's done with Python, which is a lie because the ESMValTool is actually written in multiple languages. Diagnostics are written in multiple languages, including NCL, R, Julia, and obviously Python. And links to the continuous integration testing. We'll get to these when I get to the car, and so on. So as well, we have Gitter as well. Gitter, where's Gitter here? Gitter is a channel of communication between the developers and whoever actually wants to join the ESMVal group. It's kind of a chat. It's a GitHub chat. If you don't know what Gitter is, just go there and can pop questions and bug people. Right. So modern software package is pretty much like a car, and we are, we're modest enough to say that our project resembles a Porsche because Porsche is a performance car, and we call ourselves a performance software package. So the main elements of a software package. You get the people that develop it, And these are the developers, and they are actually the drivers of the car. And these are the people that develop the diagnostics. And these are the people that come up with the science, and they say, I want to implement this science that I worked on. Just a second. And I want to implement it in ESMValTool, and I want my science to be available to others. So these are the main drivers. And this is the whole community, the whole scientific community. And then you get the users that come along for the ride. They're actually the passengers. They get to use whatever the developers have worked on, and then they may later become developers themselves because they use it and they like what they're getting out. You know, they like the results and their plots. And I say, well, I can actually improve this, and I can do this myself in a new diagnostic. So these are the and it's the manufacturers, the car manufacturers, which are us, the software engineers, that the core developers that are working on this. But I'm not putting myself in here. And then you get number one, which is the main engine of the software package, which is ESMVal Core. This is a pure Python, and you've seen this plot from Axel. This is a pure Python package that does the core analysis, the core data crunching. So when you get the data in and you want to apply a set of standardized calculations on the data and then analysis routines on the data. So these are all stored in ESMVal Core. They range from, you know, regrading, masking, level selection, all these things that can be done at the beginning before you run your diagnostic, and they are highly optimized. Well, we're proud to say, you know, we're kind of, you know, there are bits that we can still work on. There's optimization issues, but as you heard from Axel, you know, this uses state-of-the-art libraries like Iris cubes are the main data standard, and then you get the use of modern tools like Dask, for instance, to make the calculations lazy and don't use too much memory and make them faster. You get all sorts of other tricks that are hidden. But yeah, this makes it much faster. Thanks, Hazel. So this is the engine, and then you do get the inputs that the user needs to plug into it to make the other thing run. So that would be the recipe and the configuration, and you've heard the recipes. What the recipe from Axel and so on. So you know that. Documentation, as you've seen before, yes, the documentation is a main part for the software package, and the endpoint is diagnostic. You need to write your own diagnostic and get the information out of it, you know, your metrics and your sciencey plots. Provenance, which is the registration plate of the car, it's very important because you need to trace. You can click on the. I made this. Just flying through these. You can download the PDF and just click on the links yourself. So the provenance is very important, as you've heard before. Is you need to track what changes have been made to the data and how to repeat the analysis. You know, you have all the parameters in there stored in the file, in the provenance file, that allows you to repeat the analysis. And something that I'm very proud of is that we actually have a solid continuous integration. So every time somebody makes changes to the code and introduces new features, the risk is there that things may break. So we have these automated testing, this automated testing infrastructure that monitors that things don't break. So we have two continuous integration platforms that we're using. We're using Circle and GitHub Actions. And GitHub Actions is nice because you can just go here for as this one commit, and you get to the test results. You can run on multiple Python versions and multiple OSs as well. So we have Linux and OS X. And there's more here. Yes. Yeah. So I invite you guys to download the PDF, or actually just go to the ESMValTool GitHub page and have a look. And yeah, just click on the links, familiarize yourself with the stuff that you have not used it before. And we're always open for. Oh, and we also have a very nice tutorial that you may want to take if you want to learn. So yeah, we're always open for questions. That you just go to GitHub and ask questions and open issues. Just click on issues and ask questions. We're friendly. Yeah, that's it for me. Did I go over time? I hope not.
Yeah, it's okay. It's okay. It's good. It's all good. Thank you. Thank you. Well, there's no real question. There's more like a question. Is a joke from Colin. Why a Porsche and not a DeLorean? But I'm not sure you really need to answer the question.
Well, DeLorean didn't sell well at all. It was a complete flunk when it came to marketing. When it came to marketing, so no.
that's the answer. Yeah. Excellent. All right. Okay. Thank you. Thanks so much. I think we are moving to the last talk of this session, which is from Klaus Wyser from SMHI. Klaus, are you with us?
Yes, I'm here, and I try to get started here.
Yeah, can make full screen. It will be perfect. Excellent.
Okay, so this is some work, or this is work that we did a while ago already, so it's not pure fresh, but still I think it could be quite some interest for some people here who are analyzing CMIP6 simulations and comparing them against CMIP5. And this is an interesting finding that we did a while ago when we have published these results already. So there is a paper on that. This is a plot from a recent publication by Claudia Tebaldi about scenario MIP, and I'm sure many of you have seen that before. It basically just illustrates that the CMIP6 future scenarios are a bit warmer than what we have seen in CMIP5. This is a multi-model assessment, and there's some discussion on that in the paper as well. So, but let's go back a while. So when we did the simulations, actually, so we made the first plots, and we made a plot when we put the same temperature, global mean temperature, from CMIP5 simulations that we had against the new CMIP6 simulations. And we were quite surprised that there was such a big temperature difference. I mean, it was exceeding 1 degree for the warmest scenario. And the question is then we scratched our head and said, oh, how are we going to tell that to our users? And to how can we explain that there's such a big temperature difference between these models? And I mean, part of the explanation was then that, okay, it's the climate sensitivity. I mean, we all know climate sensitivity has increased in some CMIP6 models at least. And in our model, we have measured that and seen that it went up from 3.3 to 4.3. So sure, that explains we get a warmer CMIP6 projection, and so we are done. So finished. But that's only half of the story, because we then said, maybe it's not only these, yes, but maybe other things have changed as well. And the thing that we looked in at is our greenhouse gases. And also this is not very new. I mean, this has been known for a while, that the concentrations of greenhouse gases that are used in scenario MIP, they have changed from CMIP5 to CMIP6. And this is just a plot of the 5 species that we use in the Easy Earth model. And you see, for example, here that the CO2 has increased while methane has decreased. So the solid lines here are always for the CMIP6 concentration, and the dashed lines are for the CMIP5 concentrations. And the color should tell you which kind of radiative forcing these concentrations belong to. So for example, you can compare SSP 585 against RCP 8.5, and then we saw, as I said before, CO2 has increased, methane has decreased. So we then wanted to know, I mean, what does it that mean in the model? I mean, these changes, do they matter or not? So we cannot measure the radiative forcing directly. We cannot tell if this 8.5 really is 8.5 in CMIP5 and in CMIP6. But we said, okay, let's look at the effective radiative forcing. And the concept of effective radiative forcing has been presented here yesterday, I think by Fiona already, so I don't have to say very much about it. Basically, what you do is an atmosphere-only simulation. You prescribe SST and CIs, and you look at the change in the radiation balance at the top of the atmosphere. So that's what we did in short runs, and you see here in the lower right the annual mean radiation imbalance at the top of the atmosphere. If we make this AMIP type runs, and it's fairly stable over time. So there's no trend and so on. So that's why we can live with relatively short runs and evaluate this effective radiative forcing. And what we get then is that for the say the SP5 8.5 scenario, we find an effective radiative forcing of about 9 watts per square meter. For the SSP 245 scenario, we get 4.9, and for the SSP 126, we get 2.8. So the effective radiative forcing is always slightly higher than what the number in the SSP would tell you. And okay, that's fine. We can live with that because I mean it includes the feedback in the model and everything, so that's okay. But now the interesting part comes. So when we take the same model, exactly the same model, the only thing we change are the greenhouse gas concentrations. So we take the greenhouse gas concentration from the CMIP5 model. Everything else is the same. So the model physics is the same, aerosols are the same, SST is the same, everything is the same. So the only thing are the greenhouse gases. And we redo the calculations. And now this is a surprise. So the effective radiative forcing drops quite a bit. So for SSP 585, it is no longer 9 watts per square meter, but it's rather 8 or below 8 even. So it's quite a big change here in the effective radiative forcing that we see from the simple change in going back to the older generation of greenhouse gases. And we think that this can explain quite a bit of the temperature difference. And we not only think that, but we have also made some tests on that. And these are the results that I show here. So the solid lines are the full CMIP6 result. This time I only take one ensemble member, so we have only done a sensitivity test. So solid lines are for CMIP6. And the dashed and dashed dotted lines are 2 different sets of runs where we have replaced the CMIP6 greenhouse gases with the CMIP5 greenhouse gases. Everything else is the same. So and these are fully coupled runs with the ocean coupled to it. And some of the runs have started in 1850 and others have started in 2015. But it's a full model simulation. And we see, yes, indeed. So the temperature difference that you see here to the right is the temperature difference in the year 2100 between the full CMIP6 run and the run where we have CMIP5 greenhouse gases. And you see that for the SSP 585, for example, compared to RCP 85, temperature difference is 1 degree, which is quite a lot, and which is, if you remember the first plot that I showed you, where the temperature difference was maybe 1.3 degrees or so. So it explains quite a substantial part of this temperature difference between CMIP5 and CMIP6. So this is the message here that I'd like to share with you is that yes, the CMIP6 simulations are warmer than what we have seen for CMIP5. And part of this can be explained by the higher climate sensitivity in the models, sure. But the changes in the greenhouse gases also plays an important role for this temperature difference. And that's quite important when you start analyzing the results. So you cannot just explain everything by saying, oh, the models are warmer because of higher climate sensitivity, and that's it. No, it's not. It's only also the forcing data have changed, and that has to be taken into account for impact studies or for attribution studies or for anything. There's a caveat though here, and that's all these changes and differences between CMIP5 and CMIP6 are of course model dependent. So the climate sensitivity is typically model dependent, but also these changes from greenhouse gases are highly model dependent because the effective radiative forcing depends on the feedbacks in the model, and therefore we cannot say that the numbers that we get for the Easy Earth model can be applied one-to-one to any other model as well. So there is some discussion on this topic in this Tebaldi paper as well, and there are certainly other studies coming, and some of the CMIP6 experiments are now being repeated with CMIP5 forcings. So it will be very interesting to see all that work and see where it all ends. And yep, that's what I had to say for today. Thank you.
Right, thank you, Klaus. I'm looking at the chat box. They're still talking about cars. Oh, not anymore. Okay. Colin Jones, has anyone just done a pure radiation code comparison of CMIP5 and CMIP6 data? Is this possible? LBL codes?
Well, or if you have just the radiation code, the radiative transfer code, you could do that. We don't have it for our model, but other models may have that.
Okay, and then there's another question. The groups creating the scenarios concentration must have known that the greenhouse gas concentration were different in RCP and SSPs. Or did they end up using the same forcing names? Maybe I'm not sure the question to you, but
yeah, I can just speculate on that. And I know we had a discussion on that in the Paris meeting from CRESCENDO, if you remember that. So when Malte Meinshausen was there, and some of the explanation was then that the change, for example, in CO2 is offset by the change in methane. So these two would compensate slightly, but as we show here, this is not really the case. And yeah, I don't know exactly what was the reasoning why they decided to give them the same name or why they assumed that they should be identical or not. I think if you would do this exercise, and I think they did that as well in preparing the scenarios, just run it or calculate your radiative forcing, so the instantaneous radiative forcing, I think these two end up with the same number. So I am pretty sure that's the case. But that's of course not what the model sees. So the model has all its feedbacks and it changes. So that's why we look at the effective radiative forcing, and that's then different from this nameplate that is given in the name.
Right. Okay. Excellent. I don't see any more questions. So I think that's it. That's all for today. So I'm gonna thank all the speakers again, and we managed to stay on time. So thanks to you all for that. And I don't know if Colin, you want to say a few words before we adjourn and we convene tomorrow?
I don't have any great words to say apart from that we start again at the same time tomorrow. Thanks to everyone for presenting.